Welcome back, class. It's good to be with you. We're going to be doing Ugarte, Militino, and Arnholt, chapter 4.3, talking about the continuous probability distributions. Now, the notation is very similar to the discrete, but let's take a look at it here. We're going to use x as our random variables again, and the little tilde follows a, followed by the name, and then the parameters. We will go up to 2 parameters on today's distributions. Okay, there's some notation here and some notes which is helpful. Keep in mind we're talking about PDFs, and we do say PDF, probability distribution function, probability density function, as opposed to the CDF or the PMF of the discrete case. So the integral of the PDF gives us the CDF. Keep that in mind. And okay, so we'll get into it here. The first one we're going to start off with is simple. X is a continuous uniform, so it just looks like this. For some interval from A to B, then there's equal probability over the entire interval, so you get a rectangle. Now the standard continuous uniform is on 0 to 1, and that's the deviates that R's runif command gives. Okay, so I'll just note that in passing. We'll take a look. This comes in kind of a special and surprising way, but intuitively this is very simple, and the moment generating function can be derived with its expectation invariance obtained. So pretty straightforward there, very flexible and important for random number generation, critical for that. Okay. It's also going to come up in Bayesian statistics, which we might get into at some point. Now the second one is really interesting, and as we get into this, I want to just make a preface remark here. I've got a passage I'd like to read, Proverbs chapter 25, verse 2. It is the glory of God to conceal a matter. It is the glory of kings to search it out. And you, brothers and sisters, are a kingdom of priests in the Lord's kingdom, if you have put your faith in Jesus Christ and been regenerated by His Holy Spirit, covered in the blood of Jesus, forgiveness of your sins. Now, if that's the case, and I know it is with you, then it's our glory to search out what God has put into the world. And as we dive into some of these distributions now, there's going to be some amazing and beautiful connections. And so it's not an accident. Their origin is not just happenstance, but there's a profound design underlying all these purely in the abstract realm. But when you see that they fit so well with the physical realm, it's very glorious. So I would urge you to spend a little time in meditation upon these verses here, and ask the Lord to teach you these things as we go farther into it. Okay, so I want to show you some of these things. It's very cool. Onto the exponential then. Now, we'll derive it in the following way. Okay, the exponential can be construed as the waiting time until the first outcome of a Poisson process, and that Poisson process is has a rate of lambda. Okay, so am I saying that the exponential distribution is related to the Poisson distribution? Yes. Okay. So that Poisson distribution, we laid out how it is. It's a discrete, it's a count of number of events that occurs in some homogeneous interval, okay? Well, as you're waiting for those events to occur, the length of time for the next one to pop follows an exponential distribution, and we're going to prove this, okay? That's really interesting. Now, speaking a little more generally, this just turns out to be a good model for lots of things. So let's see how that works out. Okay. peeking over into our textbook, let's go. Oh, here it is. Okay, this is page 133, and the PDF is given here. We want to prove it. Okay, now in that Poisson process scenario, we have the CDF is 0 for, this says W, but you could think of it as X. It doesn't matter, it's a dummy variable. Okay, so below times 0, there's no events that are occurring. So once those events start to occur, once we start waiting, then the events are going to occur. So the probability that we have less than or equal to W events is 1 minus the probability that big W is greater than little w. Okay, so that's straightforward. That's what we mean by CDF. Okay, now W is time. Okay, with the probability that there's no events on the interval 0 to W. Okay, that's what we mean by events start occurring after W. And that is the same as in the Poisson, which comes in right here, that there are 0 events. Okay, so this is the Poisson random variable with 0 plugged in for lambda. Okay, now we're talking of an interval. We had the rate over a particular interval is proportional to the length of the interval. That's why we have lambda w sitting right here. That's lambda times the time. Okay, and I think everything else is set. So this was in the place of the x in our Poisson. Plug it in. The zeros are going to go out, so this is my CDF, big F of W. Now to go from CDF to PDF, we just take the derivative. So derivative, 0 goes out. We're going to bring down the lambda, well, e to the minus lambda W comes here, and then the derivative of what's inside. The W is the variable, so derivative of W goes out. Lambda is a constant in this operation, and voila, we have the PDF. Okay, excellent. Now, memorylessness property. Well, let's just, to be really explicit, let's get out of this. To be really explicit, let's come down and go, okay, here's my PDF. We got it. And I want to talk about this second property, which is memorylessness. Okay. It is equivalent to the waiting time assumption. The PDF can be derived using either one of these. And looking at it in the book, we have, think of a time interval here, going along in time, where maybe you start off at 0, and then there's some time 1, there's some time 2. Okay, so the probability that the event X occurs over here, that is past time 2, okay, turns out to be the same as the probability that X occurred past time 2 if it was known that it did not occur in this region right here. So I'm just going to rub this out. That's the memorylessness property. So let's run through that again, okay, using the notation. Probability that X is greater than t2 plus t1 given x is greater than t1 is equal to the probability that x is greater than t2. So the idea is that whether you consider this interval or not, as long as we know x occurs after here, then the probability that it occurs over here, unconditional, is the same as the probability that it occurs over here, given that x is greater than t1. Okay, that is known as the memory lessness property, and it seems kind of weird. What it's essentially saying is it doesn't remember what has happened up until that point. The probabilities are refreshed in some sense as time goes forward. Now, if you'll recall the special features of an exponential random variable, or excuse me, just the exponential curve, it's that specialness of the curve that is giving rise to this memory-less property. And we can discuss this further in class. For here, I merely pointed out. Okay, so back into the notes. The moment generating function is not too hard to derive. We will do this. And the moments, go ahead and note those. They're related to the Poisson moments, and I'm not going to get into it. There are some nice applications, particularly electronic components. Exponential has been used to model the lifetime of light bulbs. And if you have any process that follows a maintenance schedule where it's basically in the same condition as the thing goes along, then an exponential distribution could be used to model its lifetime as well. Okay, and of course it's designed to model Poisson process lifetimes. Okay, so boom, there's number 2. Moving into the third random variable, we have what's known as the gamma random variable. Now, the gamma is, you can think of it as a generalization of the exponential. So, if x is the waiting time until the next outcome of the Poisson process occurs, the gamma is the waiting time until the alpha outcome of Poisson process, okay? And again, the Poisson process has parameter lambda. Okay, so the waiting time is continuous, and it just has to be greater than 0, just like the exponential. And so we're going to go ahead and see how this is derived. It's got a funky looking distribution, including this weird gamma function down here. So if you'll recall from your calculus, you may have seen the gamma function. Let's go ahead and go to it. Oh, I didn't look at the graph of exponential. We'll get into the graph. Okay, so there's a function called a gamma function, which I'm not going to go into it at the moment, but I want to note it's essentially a continuous version of the factorial function. So its key properties are listed here, and if you have a positive integer n, then gamma of n is n minus 1 factorial. Its graph looks really funky because if you go with the factorials, 0 factorial is 1, right? 1 factorial is 1, so and then 2 factorial is 2. Okay, so we pop up here. 3 factorial is 6, and this thing just goes, you know, tremendously. So the gamma function, it hits these points, but it's got values in between, and it's not a nice smooth curve, but actually it does like this jitter, kind of goes wild. but it does hit at those points. So that's how it behaves. And it has this property then: if you take gamma of alpha plus 1, that's equal to alpha times gamma of alpha. That's why the factorial representation is debited by 1. And it has this really interesting property: gamma of 1/2 turns out to be rad pi. It's amazing. Okay, so let's just take a look at the derivation. I'm going to go through it quickly, so you might need to slow down and check it out yourself. But in the same way as the exponential, the CDF here, W is time, is the probability that the random variable is below some fixed little w of time, which is 1 minus probability big W is greater than W. Okay, so nothing problematic there. So converting this time issue into the gamma case now, or excuse me, into the Poisson, that is the probability that fewer than alpha outcomes occur in the initial interval of time 0 to W. Okay, so here's little w. We have 0 to W, so we must have less than alpha outcomes, and then the alphth outcome is going to occur somewhere after W. Okay, so this is the Poisson random variable, and we're going to take alpha running, k running 0 to alpha minus 1. Remember, alpha in this case is an integer. Okay, got that. So k is just a dummy variable. It was x in the previous notation. Good, so this is what we've got. Now we need to take its derivative. So it should be a relatively straightforward process, but there's some detail. So working it through, derivative of CDF gives me the PDF. And for the first move, I'm taking the derivative with respect to W. So I've got a product here, need product rule. So 1 comes down, D2. We're going to bring e to the minus lambda w times derivative of minus lambda w with respect to w is minus lambda. That comes here. 2d1, so e to the minus lambda is here. Derivative of this guy, k should come down times lambda w. Derivative of what's inside should give us lambda. Okay, we got that. K factorial hangs. Summation is intact. We're just adding everybody up. Okay, good. And this 1 goes out. Next move, let's see, we're going to factor out e to the minus lambda w. Pull that out here. Okay, and then I've got, let's see, we're going to move this term in front, k lambda w k minus 1. We're going to put this term second. We've got lambda w to the k here. And we're putting the minus in front. Okay, next up, the big move to go next is we're going to take the k equals 1 case. So when we do that, for the k equals 0. K equals 0, this term's going to go out, so that's going to give me a 0. And this term here, that k is going to go to 0, so this whole term goes to 1. So I have a minus lambda over 1. So minus lambda over 1. And then keep in mind that there's a negative sign out in front. So that negative in front, along with e to the minus lambda w, e to the minus lambda w. So lambda e to the minus lambda w is a single term, and we just move the index here and keep everything else the same. So that's where this term comes from. Okay, next move. What happens? Let's see, this guy drops, this guy's here. Alright, we're going to take the k factorial and we're going to break this into 2 terms. So that k is going to cancel with the first k in the factorial, and on the right it just goes down. Whole purpose, we want to do a telescoping expansion of this series. When we do, plugging in the K, you're going to get pairs now. Here's a pair, all the way up through the highest pair. And we note that these 1 factorial terms in the bottom cancel. The 2's are going to cancel. Everybody cancels except the first and the last term in that expansion. And so we drop them down here. Okay, now this term is going to cancel with this term. And so I'm left with this guy right here, and there was a negative, so he becomes positive right there. And it looks like this. And we're essentially done. We're just going to cuten it up a little bit. Lambda times lambda to the alpha minus 1 gives me lambda. W goes there. E goes here. And this guy is a factorial, and alpha is an integer. If we allow alpha to move off of the integer and be a continuous value, then we can use the gamma function. So if you don't, and you just stick with factorial here, it's called the Rayleigh distribution. Okay, that's probably enough of that. So let's go back then to let's go back to our notes. Okay, moment generating function. There's a shortcut to derive it so that the work is not nearly so bad. But here it is. The PDF we've obtained, and I'm not going to study it too much for now. We have expected value and variance. Applications are many. We've got the Poisson process, for example, waiting time until alpha jet engines malfunction or alpha accidents at an intersection occur. And quite frankly, it just gives you these skew right curves. And so it's a useful model for a variety of situations. Let's take a look at R and see how these pop in. Let's go. Okay. As a subcase of the gamma is exponential, all the scripts that I'm going to use are similar to this, so I want to just run over this script. It looks like there's a lot there. It's very, very simple. First line says, give me some x values that I can plot on. Okay, so I got x. It's just a sequence from 0 to 5. Okay, there's 200 observations in it, but you could change that. So that gives me my x-axis. Now, I need to compute the values for the exponential, and I'm going to use a parameter 0.5. DEXP says give me the densities for the exponential random variable. 0.5 is the lambda parameter. Okay, x is the value you want to take it at. So if I did this, and I didn't do it at x, but I just do it with, let's say, 1, then it's going to give me the exact density, that's the height of that curve, at the 0.1 for parameter lambda 0.5. However, we want to do a whole bunch of them so we can plot it, so I'm going to run that. And I want to plot 2 other curves, namely for different parameters of lambda. So let's run that stuff. Got those dudes. Now, I have 3 plot commands. They're all the same, but once you make a plot, let's just run it. Okay, margin's too large, so tighten that up. Once I make a plot, then to overlay on top of that plot, what we need to do is use the lines command, and we've probably hit this in class. So type is, do you want points, do you want lines, what do you want? Width, the default is 1, I'm expanding that to 3. Line type, we'll do some dotteds next. color blue, label the x-axis, label the y-axis, and then I have the main equals the title there. Okay, and similar for the lines commands. And very cool, I'm going to put a legend on as well, so you can read that legend command and see what happens there. Once I'm done, I've got my 3 curves, and you can see that they all have that basic exponential shape, but as you vary the parameter, it changes. Now, we have very similar for gamma. So the first one, I want to make a plot for the gamma here. And we'll notice that alpha's fixed at 2. So that means that it's the waiting time until 2 events in my Poisson process occur. Okay? So if lambda, the rate, is 5, then we have this big spike. So most of the time is around here, and then it goes off longer. If lambda is 2, then it's not as big. If lambda is 0.5, so you can see the relationship here. If I were to increase, I'd get a larger peak. And again, this can be used to model other scenarios that may not be known to follow a Poisson process time, but we just need a skew right curve. Okay, it's useful. That's called distribution fitting. Let's look at a different gamma graph and hold lambda fixed. Again, the scripts follow the same form as that exponential I just covered. So when I hold lambda fixed, we can see the behavior here. All right, great. I'd like to go back then into the book. And, oh, here's a note. I feel like it's not a good idea to call your gamma distribution with capital Gamma because we've already reserved that for a gamma function. So in our class and in R, we're always just going to call it gamma. That'll avoid confusion.